Welcome back to the deep dive. Today, we're immersing ourselves in something really fundamental. It's chapter 44 of the Feynman lectures on physics. We're talking about the laws of thermodynamics.
Yeah, foundational is the right word. This stuff governs, well, pretty much everything energy related.
And for you, our learner, think of this chapter as a crucial bridge. We've talked about molecules buzzing around, right? This chapter connects all that microscopic chaos
To the big picture, things we actually see and measure, like temperature, pressure, heat flow.
Exactly. And our mission here isn't just memorizing formulas like PV and RT30 or something.
No, not at all. It's about getting the intuition. Why does energy stick around, but why is it so hard to use perfectly?
Okay, let's unpack this. Starting with maybe the most basic idea, energy conservation.
Right. The first law of thermodynamics, Feynman really presents it as like bookkeeping for energy. You have this thing called internal energy. Let's call it deuterium. Think of it like the cash in your system's bank account.
Okay, the internal energy is the total amount.
Yeah. And if that amount, loyal, changes. Well, the change, delta U, has to come from somewhere. Only two ways. Either you added heat to the system, that's delta Q.
Like making a deposit.
Exactly. Or work was done on the system, delta WUR. That's another deposit.
So the change in your energy bank account, delta U or, equals the heat added, delta Q dollars, plus the work done on it, delta WA.
Precisely. Delta U plus delta W2, or in the sort of calculus way, dW plus dWAR.
It sounds simple, but it means energy doesn't just vanish. It just moves or changes form.
That's the core message. And Feynman makes it really physical. Think about compressing a gas with a piston.
Right. You push down on the piston.
Doing work on the gas, physically pushing those molecules.
They start moving faster, hitting the walls harder.
Yep, that's the internal energy, dollar going up. We see it as pressure increasing, and usually the temperature rising too. It gets hotter.
That makes the connection clear. Mechanical work turns into internal thermal energy.
But then there's the rubber band. That one's a bit more subtle.
Yeah, that example. If you stretch a rubber band really fast, it actually gets warm.
Work done on the band increases its internal energy, which we feel is heat. That part fits the pattern.
But the weird part, if you take a rubber band that's already stretched out and you heat it,
It contracts. It pulls back,
Uh-huh.
which is totally the opposite of what most materials do when you heat them.
So how does the first law explain that? It seems backward.
It still holds. The key is you have to look inside at the molecules. Rubber isn't like a simple gas or solid. Feynman describes it like long chains of molecules, kind of like a jumbled bowl of spaghetti.
Okay, tangled chains.
When you stretch the band, you're pulling those chains, forcing them to line up. You're creating order out of chaos.
That takes work, so the internal energy goes up. Makes sense.
Right. But the spaghetti wants to be tangled. That's its natural, high-probability, disordered state.
Ah, so when you add heat to the stretched band,
The heat gives the molecules energy to jiggle more, to fight that alignment. They want to go back to being a mess.
and tangling up pulls the ends of the band closer together.
Exactly. The heat energy is used to increase the disorder, the randomness, and that macroscopic effect is contraction. It's fascinating.
So that really connects the structure to the thermodynamics. Okay, so the first law is solid. Energy is conserved, but we know things aren't perfect. When I stretch that rubber band, some energy becomes heat due to friction, right?
Always. A little bit, anyway. Or air resistance, internal friction.
And I can never get all of that energy back as useful work. Why not? If energy is conserved, where's the limitation?
Ah, now you've hit the second law of thermodynamics. This is the big one. It's the law that introduces, well, limits and direction.
Direction, what do you mean?
The first law says energy is conserved. The second law says its quality tends to degrade. Processes generally only go one way.
Like friction.
Friction is the perfect example of what we call irreversibility. You take nice organized motion like sliding a block.
And it turns into heat.
Right. Random, chaotic jiggling of molecules in the block and the surface. That's disorganized energy.
And you can't just magically gather all that jiggling back up and make the block slide again.
Not spontaneously, no. Once energy becomes disorganized heat, you can't fully reorganize it into useful work without paying some other price elsewhere. It's a one-way street, mostly.
So the second law is kind of like an impossibility theorem. What's the core statement?
Carnot's hypothesis is central here. It basically says it's impossible to build an engine that just takes heat from one place at a single temperature and turns all of it into work in a repeating cycle.
You can't just suck heat out of the air and run a car forever.
Nope. You always need somewhere colder to dump some waste heat.
Okay. And there are those two classic ways of stating the second law.
Yeah, historically they came up slightly differently but mean the same thing. First, heat doesn't just flow on its own from a cold thing to a hot thing. Seems obvious, but it's fundamental.
Like ice doesn't make your warm drink hotter.
Right. And the second one, more about engines. You can't build a cyclical engine that takes heat from just one source, one temperature reservoir, and converts all that heat into work. Some heat must be rejected.
Which means any real engine needs like 2 temperatures to work between.
Exactly. You need a hot source, call its temperature T dollars hours. The engine absorbs some heat, Q dollars from there.
Okay.
Heat intake. Then it does some useful work, $1. But it must dump some leftover heat, $2, into a colder place, a cold sink, at temperature $2
And the work you actually get out is just the difference.
Precisely. $2 equals Q1, Q2 LR. The work is the heat you took in minus the heat you had to throw away.
So T2 is like the unavoidable waste heat.
It's the price of admission for getting any work done using heat. You want high efficiency. You need to make $2 as small as possible compared to Q volume.
But you can never make it 0 unless...
Unless your cold sink, $2 was at absolute 0 temperature, which,
Yeah.
well, brings its own challenges.
Okay, so real engines are stuck with this waste. To figure out the best possible engine, we imagine an ideal one.
The reversible engine, yes. It's a theoretical concept, a thought experiment.
We know real processes have friction, they're irreversible. What makes this theoretical one reversible?
It means every step happens incredibly slowly, with only infinitesimal differences driving it. Like, heat only moves if the temperature difference is vanishingly small. The piston only moves if the pressure difference is tiny.
So you could, in theory, run the whole process backward just by changing those tiny differences slightly.
That's the idea. If you run it backward, it becomes a refrigerator moving heat the wrong way, but it leaves the rest of the universe unchanged. It's the peak of perfection, thermodynamically speaking.
Here's where it gets really interesting. This perfect reversible process is embodied in the Carnot cycle. Can we walk through that, even without the diagram?
We can. Imagine we have our ideal engine, using a perfect gas inside a cylinder. 4 steps.
Step 1.
Isothermal expansion. The cylinder is touching the hot reservoir at temperature $1. Isothermal means the temperature stays constant.
So the gas expands does work. But to keep it hot, it must be drawing heat in from the reservoir.
Exactly. It absorbs heat Q1 at temperature $2.
Okay, step 2.
Adiabatic expansion. Now we insulate the cylinder. Adiabatic means no heat gets in or out. The gas keeps expanding.
If it's expanding and doing work but no heat comes in, its internal energy must drop.
Correct. It uses its own energy to expand, so it cools down. It keeps expanding until it reaches the lower temperature, T2.
Got it. Now we need to get back. Step 3.
Isothermal compression. We put the cylinder in contact with the cold reservoir at T2. Now we push the piston in, doing work on the gas.
But we want it to stay at T-totals. If we're compressing it, it would tend to heat up.
So it has to dump heat out. It rejects that waste heat, $222, into the cold reservoir at T2.
And the final step gets us home.
Step 4. Adiabatic compression. Insulate it again. Keep pushing the piston in. Work is done on the gas.
And since no heat can escape, its internal energy goes up, temperature rises.
Right back to the starting temperature T1 and the original volume. The cycle is complete. It can run again.
That's quite a cycle. Seems very abstract, though. Why is this theoretical engine so important if we can't build it?
Because of what Carnot proved about it. Carnot's theorem. It's huge.
Okay, what does it say?
2 things, really. First, no real engine operated between the same 2 temperatures, T1 and T2, can possibly be more efficient than this ideal reversible Carnot engine. It sets the absolute upper limit.
Nothing can beat the perfect cycle.
Nothing. But the second part is maybe even more profound. All reversible engines running between the same T and T have the exact same efficiency. It doesn't matter what's inside a perfect gas, steam, rubber bands, anything.
Wait, the efficiency is universal? Doesn't depend on the material at all?
Not one bit. As long as it's reversible and operating between those specific temperatures, the efficiency is determined solely by the temperatures T and T.
Wow. So the limit isn't about clever engineering. It's built into the universe somehow. It's like a cosmic yardstick.
It absolutely is. And using that perfect gas model in the Carnot cycle, we can figure out what that universal efficiency is. It leads to a really crucial relationship. The ratio of the heat rejected, Q222s, to the heat absorbed
Q221
is exactly equal to the ratio of the absolute temperatures, T2TT10.
Right.
So T2T10 equals T2T211, Only holds for a reversible cycle, remember?
That ratio 222Q1 equals T2T11, that seems really powerful if it's universal.
It changes everything about temperature. Before this, how do we define temperature? Like how much mercury expands in a tube? It was kind of arbitrary, tied to a specific substance.
Yeah, degrees Celsius or Fahrenheit are based on water freezing and boiling or some mixture.
But this Q2Q1 ratio for a reversible engine is the same for any substance. It gives us a way to define temperature that's completely independent of the properties of any specific material. It's based on fundamental thermodynamics itself.
So we can define temperature using heat engines.
Yes. We create the absolute thermodynamic temperature scale. We essentially define temperature, T dollars, based on how heat flows in these ideal engines. One way to formalize it is to say heat transferred reversibly is proportional to temperature, maybe $2 is T, whereas the $. Is some other property.
We'll get to S in a moment, I believe.
We will. But using this thermodynamic temperature, the efficiency of that Carnot engine we talked about, 2dBq11, becomes super simple. Since $1 equals Q on Q22 and a 222D11, it efficiency is 21 Q221 Q2. The efficiency is 12221.
Yeah, this equals $1, 22.
10, 1, Z221.
Yeah.
And this formula is universal. It shows you immediately why you can't get 100% efficiency unless 2222 is absolute zero. 0 Kelvin. As long as your waste reservoir is above absolute zero, T2T11 is positive and the efficiency is less than 1.
It all builds so logically, which brings us, I think, to that Sikio you mentioned, the final big concept in the chapter, entropy.
Entropy, $6. Yes. This is the quantity that really embodies the second law. It quantifies that irreversibility, that directionality we talked about.
How is it defined? You hinted at QMOQO's design.
Almost. The change in entropy. $. Is defined as the amount of heat added reversibly, dQrev, divided by the absolute temperature, Teneva, at which it was added. So dQrev, dQrevT.
Heat added reversibly, divided by temperature. And it's a state function, like pressure or volume.
Yes, that's crucial. The entropy of a system just depends on its current state. It's temperature, pressure, volume, not how it got there.
Okay. So what does entropy do? What are the implications? Especially when we look at the whole universe, not just the engine.
This is where it gets profound. Let's consider the total entropy, the change inside our system, plus the change in its surroundings, like the hot and cold reservoirs.
A whole setup.
Right. If a process is perfectly reversible, like our ideal Carnot cycle, the total change in entropy for the entire world is 0. Delta S total is E's total. Entropy is conserved in ideal reversible processes.
But real processes aren't reversible.
Exactly. For any real irreversible process, friction, heating things up, heat flowing spontaneously from hot coffee to cool air, anything that actually happens on its own, the total entropy of the universe increases.
Always increases, never decreases.
Never decreases. Delta S total, it only stays 0 in that unattainable ideal reversible case. In reality, it always goes up.
So every time anything happens naturally, the total disorder of the universe inches up a bit.
That's a very good way to put it. Entropy is deeply connected to disorder, probability, the number of ways energy can be arranged. There are vastly more ways for energy to be spread out randomly, high entropy, than to be organized neatly, low entropy.
So the universe is just naturally drifting towards the most probable, most mixed up state.
That's the essence of the second law, captured by entropy. It gives time its arrow, things break, they don't unbreak. Heat spreads out, it doesn't spontaneously concentrate.
Wow. Okay, so this one chapter basically lays down two incredibly powerful, unshakable laws governing everything.
Pretty much. First law, energy is conserved, the total amount in the universe is constant, dd equals dq plus dd.
Second law, entropy increases. The total disorder, the S of the universe, is always going up, $0. So what does this all mean? We started with simple energy conservation, looked at ideal engines to find limits, defined temperature itself thermodynamically,
and arrived at entropy, which tells us that while energy is never lost, its usefulness, its ability to do work, constantly degrades as it spreads out into disordered heat.
The quality decreases even if the quantity is constant.
That's a good summary. The key takeaways for you to hold on to. The first law equation, d dollar equals dq plus d dollar. And the big idea of the second law. Total entropy never goes down, delta S total squirtle. This dictates why engines need hot and cold parts, and why perpetual motion machines of the free energy kind are impossible.
And thinking about that relentless increase in entropy, it leads to a final provocative thought. The sources mention the third law of thermodynamics, which wasn't fully detailed here, but suggests something interesting. That at absolute zero temperature, $2 is dollars, the entropy of a perfectly ordered crystal would actually be 0. Perfect order.
The theoretical baseline.
But if the second law says the entropy of the universe is always increasing, always moving towards maximum disorder, does that imply we can never actually reach that state of perfect order at $T$? Is absolute zero fundamentally unattainable because the universe is constantly messing things up?
That's a deep question rooted right here in these laws, something to mull over.
Indeed. Well, thank you for joining us on this deep dive into the laws that shape our thermal universe. We'll catch you next time.